Welcome to the deep dive. Today, we're really digging into the world of semiconductors, specifically this whole GPU gold rush happening around 2025.
That's right. You shared some great articles looking at why these chips are suddenly so critical, the real challenges in making them, and just the massive investment flooding in.
Yeah, and our mission today is to unpack all that complexity, pull out the key insights for you listening.
Definitely. So whether you're, say, prepping for a meeting, trying to get a handle on this field, or you're just curious about the tech shaping everything, well, we're going to break it down, make it clear, make it engaging.
We'll be using insights from that semiconductor scramble overview,
Yeah.
the announcement about the 4IR ecosystem, and several deep dives into the GPU market itself.
And you mentioned one source had a great analogy.
Yeah, it really clicks for me. Silicon is the new oil, and GPUs, they're the modern-day drilling rigs. We need to explore why that feels so true right now in 2025.
It's a powerful image. But before we get into the silicon nitty-gritty, just a quick word about our sponsors. This deep dive is brought to you by blockchaincompany.info, our media hub, and sponsored by the 4IR utility token and 4IR GPT. You can explore the whole 4IR utility ecosystem over at 4IRtoken.com.
And 4IRGPT.com, that's their platform for AI knowledge exchange, right, where people can trade insights.
Exactly. It's a really interesting space where you can actually, monetize your expertise, turn your domain knowledge into value by creating effective prompts.
Yeah, and for you listening, if you've got that kind of sharp insight, check out 4IRGPT.com. They're offering 10 free credits just for signing up. It's a chance to see how you can make your knowledge work for you.
And it's a great tool for YouTube channel owners too, potentially boosting income, amplifying reach. Definitely worth exploring at 4igpt.com.
Okay, perfect. So let's dive in. These AI class chips, what exactly makes them so incredibly valuable right now?
Well, it really comes down to a fundamental shift in computing driven by AI. These modern GPUs, they aren't just powerful graphics cards anymore. Their architecture is specifically designed for parallel computation.
Which is key for AI workloads.
Absolutely essential. Think about things like tensor cores. They're built specifically to speed up the matrix math that's, at the heart of deep learning. That's crucial for training these huge AI models.
And the memory.
Massive memory bandwidth. You need to shuttle data incredibly fast to keep those powerful cores busy. It's this whole specialized design that makes them indispensable.
So it's not just raw speed, it's the type of speed tailored for AI. And you see the demand just exploding with all these AI breakthroughs. Chatbots, autonomous systems.
Precisely. AI isn't sci-fi anymore. It's being deployed everywhere. Natural language processing, autonomous driving, they all lean heavily on this parallel processing power. Only these advanced GPUs can really provide efficiently. That broad applicability is driving the value.
Okay, so the demand is, well, intense. But the sources talk about a semiconductor scramble, chips being scarce. What's the bottleneck? Why can't we just make more?
That gets us into the sheer complexity of manufacturing. We're talking about next-gen process nodes features measured in nanometers, a few billionths of a meter.
Like drawing with atoms, basically.
Pretty much. It pushes physics and engineering to the absolute limit, and the cost.
Yeah.
Building one advanced fab, one factory, you're looking at tens of billions of dollars.
Tens of billions. Wow. That puts it in perspective. More than the GDP of some countries.
Exactly. And it's not just money. The whole supply chain is incredibly intricate.
How so?
Well, think about it, from getting the ultra-pure raw materials for the silicon wafers all the way through to the specialized equipment needed for every tiny step. It's a fragile ecosystem.
And we've seen disruptions there recently.
We have global events, sure, but also just relentless demand. Data centers are running these chips 204/7, burning through them faster, needing replacements and upgrades constantly.
And then, layered on top of all that, geopolitics. The U.S.-China tension, this idea of tech sovereignty. How's that playing out?
It's huge. National security is now deeply tied to chip production. Tensions lead to export controls, trade restrictions, countries trying to limit who gets access to the most advanced tech.
Which fuels this push for tech sovereignty, like nations wanting control over their own chip supply.
Precisely. Everyone wants to control their critical tech supply chains now. For economic reasons, for security reasons.
So countries are trying to bring manufacturing back home, or at least to allied regions. Is that where the TSMC Arizona fabs come in?
Exactly. That's a prime example. Huge investments like TSMC in Arizona are about diversifying manufacturing, reducing reliance on potentially vulnerable regions.
Governments are actively shaping this with policies then.
Absolutely. Policies create strategic partnerships, but they also create restrictions. And that, unfortunately, can lead to fragmentation of the global supply chains that took decades to build.
It sounds like a massive balancing act. Exploding demand, huge manufacturing hurdles, geopolitical pressures.
Yeah.
No wonder Silicon Valley and Wall Street are pouring money into this space.
Right. If you connect the dots, the AI revolution promises enormous growth. Investors see that. They see the potential for huge returns, so they're funneling record capital into R&D, into new manufacturing capacity.
They seem pretty confident in the leaders, too, like NVIDIA, especially with things like their new Blackwell series coming out.
Well, NVIDIA has built tremendous investor confidence. Blackwell isn't just another chip. It's seen as a significant leap in architecture, better power efficiency, which is critical.
Especially in massive data centers.
Exactly, and enhanced AI cores. This kind of innovation just fuels more enthusiasm, more investment, and this intense race to secure the IP and, crucially, the production capacity.
Let's zoom in on Blackwell for a second.
Yeah.
What makes it so significant in this gold rush context?
It's really engineered for the next level of AI demands. It's not just faster, it's more efficient, more processing per watt of energy. That matters hugely at scale.
And the AI cores are even more specialized.
Right. Optimized for the complex math underlying the latest AI models. Its existence just highlights this relentless drive for more power, more efficiency, to fuel whatever comes next in AI.
Okay, and the TSMC Arizona fabs, you mentioned onshoring, diversifying. What are the other strategic angles and maybe the challenges in getting something that complex running?
Strategically, it's about resilience for the U.S. and its allies. Less dependence on Asia for the absolute cutting edge. It mitigates geopolitical risk, secures supply.
But it's not easy to just spin up a fab like that, is it?
Oh, definitely not. The scale is immense. Construction takes years. You need a whole ecosystem of suppliers for materials, specialized equipment, and you need a highly skilled workforce. Training people takes time. It's a monumental task to replicate that leading-edge capability quickly.
So even with all this money pouring in, these big projects, chip shortages aren't just going to vanish overnight.
That's the reality. Demand, especially AI-driven demand, is still outpacing capacity growth. Even the big players struggle to get all the advanced chips they need.
So what's the strategy? Just build more of the same faster.
It's sort of two-pronged. Yes, expanding current capacity as fast as possible to meet immediate needs, but also a huge focus on innovation in production itself. Things like advanced packaging, integrating multiple chiplets into one package for better performance, or heterogeneous integration, mixing different types of processors on one chip for specific tasks. It's about getting more out of the silicon we can make.
Feels like we're on the edge of some big shifts in chip design and manufacturing. The sources mentioned going beyond traditional GPUs. What are some of those alternatives being explored?
Yeah, that's where it gets really interesting. We're seeing dedicated AI accelerators chips designed purely for specific AI tasks, often much more efficient for those jobs than a general GPU.
Anything else?
Neuromorphic chips inspired by the human brain. They aim for incredible energy efficiency and parallel processing, good for certain real-time neural network tasks. And even quantum-inspired processors are being researched, looking at totally new ways to compute for really complex problems.
Wow, a whole range of different approaches. Do you think these might eventually merge, maybe into one unified chip?
That's definitely a long-term possibility people are exploring. Architectural convergence, blending CPUs, GPUs, AI accelerators onto one chip. The goal would be a highly adaptable solution, efficient across many different tasks. Performance gains, power savings. That's the dream.
It's incredible how AI has just completely changed the game for GPUs.
Yeah.
It wasn't long ago they were mostly for gaming, right?
Yeah.
How did that shift from like luxury item to critical infrastructure happen so fast?
It really was remarkable. Basically, training these enormous AI models, billions, trillions of parameters, just overwhelmed traditional CPUs. They needed the massive parallel processing GPUs offered.
And then using the AI models too, inference.
Right. As AI moved into real-world apps, you needed real-time decisions. That needs low latency, high throughput. Again, GPUs, especially with things like tensor cores, were perfectly suited.
Those specialized cores are key, aren't they?
Absolutely. They dramatically speed up the core math of deep learning. That efficiency is what made GPUs the workhorse. And you see it in the numbers NVIDIA's Blackwell orders hitting something like $30 billion in a quarter. That tells you how central these things are now.
Okay, so demand, manufacturing, geopolitics.
Yeah.
Let's circle back to that SAN to server journey. Where are the specific bottlenecks, the real choke points holding things up?
If you map it out, three areas really stand out. First, and maybe biggest, is photolithography, specifically EUV extreme ultraviolet lithography.
That's ASML, the Dutch company.
Exactly. They're essentially the sole supplier of the machines needed to etch the tiniest features on the most advanced chips. It's incredibly complex technology.
So if ASML can't make enough machines, the whole industry slows down.
Pretty much. These EUV machines are unbelievably expensive, hundreds of millions each. Their own production is limited, lead times are super long, and you need intense expertise to even run them. It's a major bottleneck.
Wow. Okay, what's the second major choke point?
Advanced packaging. It's not just about the chip itself, but how you assemble and connect multiple chips or chiplets together into the final product, especially for high-performance AI.
So getting the chips connected efficiently is just as hard.
It's becoming critical. Techniques like 3D stacking, they need their own specialized infrastructure, materials, tools. And there are bottlenecks in that supply chain too. So even if you have the silicon dies, packaging can slow everything down.
Makes sense. And the third critical bottleneck.
That would be access to the absolute cutting-edge process nodes themselves. Think 2-nanometer technology pioneered by just a few foundries, mainly TSMC.
Just making things that small is the challenge.
It's an extreme engineering feat. Massive R&D investment over years, deep expertise, very few companies can do it. And even then, getting good yields meaning a high percentage of working chips is tough. Plus, transferring that tech know-how to new fabs is slow and difficult.
So yeah, definitely not just a matter of building more factories quickly. Why is it so hard to just ramp up fab construction?
Well, these aren't just factories, they're mega projects. Planning and construction take years, 3, 5, maybe more.
We mentioned the cost tens of billions.
Right. And they depend on this vast, intricate web of suppliers for everything. Pure silicon, specific chemicals, gases, precision tools. Any snag in that supply chain causes delays.
And regulations. Geopolitics again.
Absolutely. Navigating permits, environmental rules, plus the whole geopolitical angle if it's seen as a strategic national asset. It all adds time and complexity.
It really paints a picture of this incredibly fragile, complex global system. Let's dig a bit more into how geopolitics is actively reshaping chip flows. Export controls, China's response to the U.S. CHIPS Act. How are they actually changing who gets what?
It's fundamentally redrawing the map. U.S. export controls aim to restrict access to advanced manufacturing tools and chip tech, trying to slow down rivals. That directly impacts who can make the most advanced chips and who can design them.
And China's reaction.
A massive push for self-sufficiency. Huge domestic investment in R&D, manufacturing, talent, trying to build their own complete ecosystem, reduce reliance on foreign tech, maybe find alternative ways to make advanced chips using tech that isn't restricted.
So more fragmentation.
Definitely. You see countries aligning with U.S. rules, others trying to go it alone. It creates uncertainty, forces companies to navigate these shifting political landscapes, potentially disrupting supply chains.
Where does the U.S. CHIPS Act fit in all this?
Yeah, it's the U.S. trying to boost its own domestic manufacturing, offering big financial incentives, grants, tax credits to build fabs in the U.S. The goal is less reliance on overseas production, especially for critical advanced chips for economic and national security.
Is it working? Is it shifting production significantly?
It's definitely spurred announcements and investment, but building cutting-edge capacity takes years, decades even. So it'll likely complement global production patterns for a while, not completely replace them overnight. Reshoring the most advanced stuff is a long game.
Which might explain why, even with CHIPS Act money, someone like NVIDIA still relies so heavily on TSMC in Taiwan.
Exactly. TSMC just has the proven capability, the experience, the efficiency, the scale at the cutting edge right now. It's incredibly hard and time-consuming to replicate that.
So transferring that know-how is a huge barrier.
A massive one. For NVIDIA, time to market and performance are everything. Sticking with TSMC ensures they get the chips they need, at the quality they need, to stay ahead. Plus, while Taiwan has its own risks, relying only on one new, unproven domestic fab might seem even riskier in the short term. It's complex risk management.
Definitely a period of intense strategic maneuvering. Okay, shifting slightly, analysts seem to think fears of an AI spending slowdown are, quote, laughable. Why such confidence? And how is this relentless demand affecting things like company evaluations, CapEx, M&A?
Well, the thinking is that AI isn't just a trend anymore. It's becoming fundamental infrastructure. It's getting embedded in everything across industries. So the demand for the compute power, mostly GPUs, is now part of long-term strategy for countless companies, not just hype.
So it's seen as a durable, long-term demand driver.
Exactly. And the belief is continued AI innovation will only increase that demand. It's not seen as something likely to suddenly start.
And the financial impacts? Valuations? Spending?
Well, high demand plus scarce supply equals high valuations for companies involved in designing, making, or supporting these chips. It creates a premium.
Makes sense.
And it drives massive capital expenditure, CapEx. Companies are spending heavily to expand capacity, to research the next thing, and we're seeing more M&A mergers and acquisitions as companies try to buy expertise, secure supply chains, or gain economies of scale to compete better.
It's a real high-stakes race. Let's look at how the big tech players are approaching this. NVIDIA with CUD, Google with TPUs, Amazon with their chips, AMD,
Yeah.
different strategies, right?
Yeah.
How do they compare on managing risk and vertical integration?
It's fascinating, isn't it? NVIDIA's strength is that tight CUD software-hardware ecosystem. Developers know it. It's optimized. But they rely on external fabs like TSMC, which creates some supply chain exposure.
Whereas Google and Amazon are building their own.
Right. Google's TPUs, Amazon's Inferentia, and Trinium custom chips designed in-house primarily for their own massive cloud workloads. That gives them more control, lets them optimize for their specific needs, hedges against relying only on NVIDIA or others. It's more vertical integration.
And AMD.
AMD is playing it a bit differently with chips like the MI300. They're designing advanced stuff, competing hard on performance, but using external partners like TSMC. It's maybe a bet on offering high performance within a more open ecosystem compared to NVIDIA's CUDA, a balance perhaps.
So different bets on how to navigate the supply chain and ecosystem dynamics. Okay, finally, let's look beyond GPUs again. Those alternatives, wafer scale, photonic, neuromorphic chips. Could they actually ease the GPU crunch? Or will AI demand just keep outpacing everything?
That's the critical question, isn't it? These alternatives are genuinely promising long term. Wafer-scale systems like Cerebra's offer incredible density for some tasks, but scaling production and integration is still a challenge.
Photonics. Using light.
Yeah, potentially huge gains in speed and energy efficiency for data movement, maybe specific calculations. But it's early days. Integrating with electronics is tricky.
And neuromorphic. Brain-inspired.
Super energy efficient for certain tasks, like real-time pattern recognition. But they need different programming approaches, and scaling up manufacturing isn't straightforward yet.
So exciting, but maybe not ready for prime time across the board.
I think that's fair. The sheer scale and speed of AI compute demand right now is unprecedented. It seems likely that demand will outpace the maturation of these alternatives in the near term.
Meaning GPUs aren't going away anytime soon.
Probably not. The GPU ecosystem is established. It's evolving rapidly itself with things like better packaging and software. While we'll likely see a more diverse computing landscape emerge over time with specialized chips for specific jobs, GPUs look set to remain dominant for AI infrastructure for a while yet.
This has been incredibly insightful, really unpacking this GPU gold rush. So
Yeah.
just to recap the big picture, AI's massive demand is driving everything, the tech advances, the manufacturing struggles, the geopolitics, the huge investments.
Right. And key bottlenecks, lithography, advanced packaging, cutting-edge nodes are major hurdles. Alternatives are coming, but likely not fast enough to meet the current surge. GPUs remain central, at least for now.
A complex, fascinating picture.
And just a final reminder, this deep dive was brought to you by blockchaincompany.info and sponsored by the 4IR utility token at 4irtoken.com and 4IRGPT over at 4irgpt.com.
Right, don't forget to check out 4irgpt.com, grab those 10 free credits, and see how you can monetize your expertise, especially useful for YouTube channel owners looking to boost income and reach.
Definitely explore it.
Absolutely. And if you found this discussion helpful, please do click subscribe. It supports the channel, keeps you updated on future deep dives, and you'll hear about those 4IR credits giveaways too.
And maybe one final thought to leave you with. Considering the huge energy footprint and the reliance on rare materials for all this AI compute, what fundamental shifts, maybe in technology or even global collaboration, might be needed to make sure the future of AI is, sustainable and ethical, something to ponder?